Hello people, I am Hamid Reza. I would like to welcome you all to the class. It's my great pleasure being with you as a lecturer for scientific computing and simulation. As you know, the module will be delivered online until further notice. So in the meantime, please take care of yourself and your families. Today, after an introduction to the module, we will look at the principles of Fourier analysis. Let's start the module by a definition of scientific computing. In fact, we want to know what scientific computing is. To answer this question, I refer you to Scientific Computing and Differential Equations, an introduction to numerical methods. Scientific computing in this book is defined as a collection of tools and techniques. We rely on this collection to model, simulate, and solve various complex problems using advanced computing capabilities. It is interesting to note that most of these tools and technologies in scientific computing develop in mathematics, and this set of theories and techniques is called numerical analysis. Basically, scientific computing and simulation is an area of science associated with mathematics and computer science to aid modeling, simulating, and solving complex scientific problems by using computers. You might ask why we need scientific computing. There are two main approaches to gain knowledge in science. The theoretical investigation, like what mathematicians are doing, and experimentation, what is usually taken by engineers. These methods have some drawbacks. For instance, real phenomena are usually too complicated to getting them solved using trivial models. In addition, there are situations that we cannot conduct real experiments because of extraordinary costs being highly risky, so on and so forth. In such circumstances, the only solution is to employ computational modeling and simulation. Now we want to go through some applications of computing in science and technology. Scientific modeling is used in meteorology to forecast weather and study the impact of greenhouse gases on climate change. Investigating the stability of large-span bridges and skyscrapers against earthquakes and wind loads is another application of scientific computing. In situations like this, there are no second try, and modeling is the only feasible way for analyzing. In addition, the essential role of computing in the aviation industry is not hidden from anyone. Computing and simulation assist mechanical engineers in the car industry to build car prototypes and evaluate them. Modeling and simulation before manufacturing real products is the best way to prevent wasting money. After a brief introduction, let's have a look at the syllabus covered in this module. In the first part, we review Fourier transforms and then go through some of its applications in image processing and signal filtering. After that, we practically learn some numerical methods and simulation models. Now it comes to assessment. I really believe in your abilities, and I'm sure you will be able to master the teaching materials very well. In this module, your coursework represents the overall credit of the module, which is a portfolio with two parts. Teaching in this module is driven by practical work undertaken in the lab sessions. So, the first part of the assessment will be based on a lab report. In the report, you will record your learning and experimental outcomes. The second part of the assessment is a report on the result of a mini project on scientific computing and simulation that you will undertake in the latter part of the teaching block. In the last few weeks of the term, you will be provided with a list of possible mini projects on the Moodle site for the module, and you will choose exactly one of these projects to do. For further details, please have a look at Module Coursework Scientific Computing and Simulation Coursework Word file on the Moodle site. In this file, you can find information about deadlines, how to prepare your lab book, how to document your mini project, and the marking scheme. Here, I would like to appreciate Dr. Carpenter's efforts for designing and developing the module. Okay, now let's study the basics of Fourier analysis. We will use Fourier analysis for interesting kinds of image processing and image reconstruction later on in this module. Generally, you are familiar with the idea of dividing light or sound waves into different frequency components. For instance, here we can see how a beam of light is decomposed into its component colors when passing through an optical prism. In fact, waves are broken into simple components color when passing through the optical prism. This slide visually shows the concept of signal decomposition. Here, we have a complex signal X. We can see how the signal is decomposed into a group of pure components X1, X2, and X3. It is interesting to note that we can reconstruct the original signal by synthesizing its component. I mean, we can reconstruct the signal X if we add the three simpler signals X1, X2, and X3. Okay, you might ask about the idea behind wave decomposition. When a signal is decomposed, its component signals are simpler than the original signal. As a result, instead of processing a complex signal, we can process its pure components and then sum the results to obtain the final output. As an example of how signal decomposition makes the analysis task easier, try to multiply the number 2041 by number 4 in your head. Of course, the straightforward way is to decompose the number into 2000, 40, and 1. Then multiply each number by 4 and add the results. In the same way, signals can be processed. For instance, here we first decompose the input signal into its pure components, which are three simpler signals. Then each signal is processed by passing through the system to analyze them. Finally, the output is equal to the summation of the three signals, Y1, Y2, and Y3. The output signal is identical to the one produced by processing the input signal X. We also use signal decomposition technique to remove undesirable components from waves and signals, such as noise. There are two main approaches for wave decomposition: Fourier decomposition or Fourier transform, and impulse decomposition. In this module, we only focus on Fourier transform. We use Fourier transform to obtain the spectrum of signals. Suppose this figure shows the waveform of a musical signal over a period of time. The signal consists of a combination of different frequencies. Using Fourier transform, we can decompose the signal to its component frequencies that make it up. As we can see here, the original signal is decomposed into 4 signals. Each represents a tone or a specific frequency in the musical signal. In fact, using Fourier transform, we can recognize the original signal is made up of 4 different frequencies. To better understand Fourier transform, I invite you to watch a short video. You can find the full video on YouTube via the link shown here.
This sound right here is a pure A, 440 beats per second, meaning if you were to measure the air pressure right next to your headphones or your speaker as a function of time, it would oscillate up and down around its usual equilibrium in this wave, making 440 oscillations each second. A lower pitch note, like a D, has the same structure, just fewer beats per second. And when both of them are played at once, what do you think the resulting pressure versus time graph looks like? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually, which, let's face it, is kind of a complicated thing to think about. At some points, the peaks match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine wave. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. But right now, all it is a combination of 4 pure frequencies. So it seems needlessly complicated given the low amount of information put into it. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sum. So our central question is going to be how you can take a signal like this and decompose it into the pure frequencies that make it up. Pretty interesting, right? Adding up those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple paint colors that have all been stirred up together.
In mathematics, a signal can be continuous or discrete. Unlike a continuous signal, a discrete one is not a function of a continuous argument. A discrete signal may have been obtained by sampling from a continuous signal. Now we want to learn how Fourier transform works. Discrete Fourier transform is a mathematical technique that decomposes general waveforms into a series of sine and cosine waves with fixed frequencies. In this slide, we have the discrete signal n. The Fourier series breaks the signal into sine and cosine signals. As shown here, the wave is decomposed to the pure frequencies, which make it up. Fourier transform is able to analyze continuous and discrete signals. However, we only consider the discrete version because digital computers can only work with information that is discrete and finite in length. In mathematics, any sinusoidal wave is defined using 2 main parameters: frequency and amplitude. Frequency represents the number of oscillations of a wave per second. Amplitude is the maximum distance moved by a point on a wave starting from its equilibrium position. For instance, the frequency of the sine wave shown here is 2, and its amplitude is equal to 5. We had this example before. The input waveform shows how a signal changes over time. So we say the input wave is in the time domain representation. The input signal is made of 4 frequencies, and as shown here, the Fourier transform decomposes the input waveform into 4 pure sine and cosine signals, each with a fixed frequency and a fixed amplitude. This graph on the right shows the 4-component waveforms in an alternative and simple representation, which is called frequency domain. In this graph, instead of showing the waveforms of signals, we only display their frequencies and amplitudes. In frequency domain representation, each bar represents a pure waveform. For example, the first bar represents the frequency and amplitude of this pure wave. The second bar here shows the corresponding parameters of the next pure wave, and so on. So as we can see, the Fourier transform converts something very complicated in the time domain to a very simple representation in the frequency domain. Let's watch another video giving us further information about time and frequency domains. The link to the complete video is here.
This black rectangle here is the speaker, and travelling away from it through the air are waves of sound. They look very like the waves in water. As the air molecules bunch together, we get the crest of a wave showing an area of high pressure. As the air molecules are pulled apart again, we see a trough forming, showing an area of low pressure. If indeed this was water, and we were to place an imaginary ball just in front of the speaker, we could envisage how the ball would bob up and down on the waves as they pass by. Now if we draw a line showing not only the current position of the ball, but where the ball was a moment ago, and a moment before that, and a moment before that, and so on, we can actually draw a representation of the sound waveform. How could we represent this line mathematically? Well, it just so happens that there is a mathematical function that looks very much like this simple wave shape. That function is called a sine function. You may remember the sine function from your school days as having something to do with the angles of triangles. If you take the sine of this angle here and multiply it by the length of the hypotenuse, you can calculate the height of the triangle's apex. But what has this purely mathematical function got to do with the sound waves we saw before? Well, just watch this. As the angle of our triangle increases, it rotates the apex of the triangle around it in a circle. Now, if we plot all the different angles through which our triangle has rotated on a separate graph, you can see that the shape it describes looks very similar to the sound wave we saw before, which is why a sine wave is a pretty good approximation of a sound wave. But how can something so simple like a sine wave be so versatile? After all, we use sound to transfer information in speech or music. How can such a simple wave like this contain so much information? Well, the short answer is that it can't. This wave just sounds like a single tone. What can we do to make this sine wave sound a little more like something you might hear in the real world? Until now, we've looked at our sine wave as a signal that changes over time, like a floating ball moving up and down on the crest of a wave. I want to look at our wave in a slightly different way. I'm going to assume that the basic shape of our sine wave never changes. It always looks like a rise and fall over time. So, what properties of my wave can I change? There are in fact 3 properties I can change, but for now I'm going to deal with only 2 of them. We'll deal with the third in the next lecture. I'm going to change the frequency or pitch and the amplitude or loudness of my wave. So if I already know what my basic sine wave looks like, I don't really need to see the wave itself. What interests me is its frequency and its amplitude. So I'm going to plot my sine wave on a new graph. We can now see our single sine wave represented as a peak. As the frequency increases, the peak moves to the right, and as the frequency decreases again, the peak moves back to the left. As the amplitude decreases, the peak gets smaller, and as the amplitude increases again, the peak gets larger. This new way of looking at my sine wave is known as looking at it in the frequency domain, plotting the amplitude of the sine wave against its frequency, as opposed to the way we looked at it before in the time domain, when we plotted how the amplitude of our sine wave changed over time. This distinction is going to be very important to us later on, when we get deeper into what the Fourier transform does. But for now, I want to use the frequency domain to look at how we might change our basic single frequency sine wave into something more interesting. Something a little more musical. So let's go back to the sine wave we had before. Here it is in the time domain, and here it is in the frequency domain. What happens now if we add another sine wave? You can see our new sine wave represented in the frequency domain as a new peak to the right of the first one, meaning that it is a sine wave with a higher frequency than the first. The peak is smaller, telling us that it is not as loud. Now let's look at the effect that it has on our sine wave in the time domain. Now we're going to add another sine wave at another frequency, and another one, and another. Each sine wave appears as a new peak in our frequency domain graph and changes the shape of the waveform in our time domain graph. As we add more and more sine waves to our signal and begin to play a little with their amplitudes, our waveform begins to actually sound like something real. A violin, in fact, playing the note A.
This slide presents the discrete Fourier transform formulation for a given signal x. As explained earlier, DFT decomposes a wave into some cosine and sine component waves. The amplitudes of the waves are held in AK and BK respectively. Each wave has a frequency which is equal to k by n. As shown here, the input wave can be obtained by a summation of its cosine and sine Fourier components. This example here shows the DFT decomposition of a discrete signal consisting of 16 points. Here we can see how the signal is decomposed or transformed into some cosine and sine waves. For instance, k in this cosine wave is equal to 3, so its amplitude is A3 and its frequency is 3 by 16. This example shows how an input signal made of a combination of several frequencies is decomposed to its Fourier components. Fourier transform is divided into two versions, real and complex. Real DFT is the simplest and only uses real numbers. We have discussed real DFT by now. However, complex DFT is the more general form of the real DFT that represents data using complex numbers. Before discussing the complex DFT, I want to recap complex numbers. A complex number, as you know, is a number that can be expressed in the form a plus bi. A and b are real numbers, and I is the square root of -1. Here we can see how to add and multiply two complex numbers. I want to also introduce Euler's relation that establish the relationships between trigonometric and polar functions. The left-hand side expression shows a complex number in the polar form. However, the right-hand side expression shows this complex number in the rectangular notation using sine and cosine functions. We can use this equation to obtain the polar forms of cosine and sine functions and finally obtain the complex Fourier series. Okay, in this slide we have the complex DFT series written in polar form. Consider an input signal x consisting of n complex points or samples. Using this series, we can transform the input signal x into n Fourier components, which are stored in Ck. In fact, Ck stores n complex numbers. Each one determines a component wave for the input signal x. In this series, the parameter k refers to the wave number. Unlike the real DFT, which outputs two sets of amplitude, one for cosine waves and one for sine waves, the complex DFT just returns a single set of complex numbers. So this series takes a complex signal x and gets back its complex Fourier component. Transforming the original signal into its components is called forward Fourier transform. We can employ Euler's relation to obtain the complex DFT in rectangular form. Like the previous series, this one transforms a given complex signal x to its complex components. Here, we can see how real and imaginary parts of each complex component are calculated. The inverse DFT series is used if we want to reconstruct a signal x using its corresponding components, which are stored in Ck. This series, as shown here, takes Ck as the input and returns the original signal. The process of reconstructing an original signal from its components is called inverse Fourier transform. This slide shows the rectangular equivalent of the inverse DFT series in polar form. Like the polar inverse DFT, the rectangular series reconstructs the complex signal x by synthesizing its complex components stored in Ck. This slide virtually shows transforming a wave into its components and synthesizing them to reconstruct it. As I mentioned earlier, each Fourier component signal has a fixed frequency. Therefore, the Fourier transform allows us to recognize all the frequencies that construct the original signal. In previous slides, we discussed one-dimensional DFT. One-dimensional Fourier transform is able to analyze waves with just one dimension, such as voice or music waves. There are many applications which are functions of 2D or even higher space, such as images. So if we want to transform pixel values of an image, we need 2D DFT. Consider a given 2D signal stored in an n by n matrix X. The first series in this slide calculates the 2D Fourier transform. It breaks the input signal X into its frequency components. Matrix C stores these components. C is a 2D matrix where CKL stores the Fourier component for the wave number K and L. The next equation shows the inverse 2D DFT series that reconstructs signal X using its components in matrix C. 2D DFT is a powerful tool for image processing. Here we have an image that its pixel values are stored in matrix X. The 2D FFT series discussed in the previous slide can transform the image pixels and store the results in matrix C. The image here shows the transformed image in frequency domain. In Lab 1, we will practically transform a sample image based on the 2D DFT series, and then we will reconstruct it by using the inverse 2D DFT series. In addition, we will use Fourier transforms to do simple filtering of images and interesting kinds of medical and scientific image reconstruction. For further reading, you can use Digital Signal Processing, a practice guide for engineers and scientists. Okay, that's all for today. Thank you for your attention.